All right, let's get right into it. Today, we're diving deep into the science of creating materials that can handle some of the most extreme forces you can possibly imagine. We're really talking about the frontier of resilience, where scientists are basically rewriting the rulebook on what our materials are capable of. So I want you to think about this for a second. What if the things we rely on every day, our cars, our homes, the gear that protects us, what if they were no longer held back by the strength of the stuff they're made from? What if they could just take a hit that today seems totally catastrophic? That's the huge idea that's driving all the research we're about to explore. Okay, so here's our game plan. We're going to start with the problem itself, the shockwave. Then we'll see how scientists are using some seriously powerful computers and amazing experiments to basically get a slow-motion replay of materials breaking. After that, we'll look at how they're using that knowledge to build the super materials of tomorrow. And finally, we'll see how it all clicks together in one big integrated picture. Right, first things first, you can't build a better shield until you really understand the sword you're up against. And in this case, that sword is a shockwave. You know, the key thing to wrap your head around here is the speed. We are not talking about a slow, crushing force. A shockwave dumps all of its destructive energy in a few nanoseconds. That's billionths of a second. It's so fast that it causes materials to just shatter and fail in bizarre ways that your standard stress tests could never, ever see coming. It's a whole different ballgame. So how do you fight something that fast? Well, you need a way to predict what it's going to do, and that's where we turn to the digital world. We're talking about using supercomputers to create these incredibly detailed models that show exactly how a material will twist, crack, and fail under that insane pressure. But here's the catch, and it's a big one. For a long time, there was this problem called the micro-macro divide. Think about it like this. It's like trying to predict a massive traffic jam across an entire city by only studying the chemical formula for asphalt. It's impossible, right? There's this huge gap. And that's exactly the issue scientists had, connecting how single atoms behave, the micro level, to how a big slab of that material, the macro level, is actually going to hold up in the real world. And this is the breakthrough. The old way of doing things, which you see over on the left, was like having two totally separate maps that didn't connect. But the new models, they link everything, from the atomic level to the grain structures in the middle, all the way up to the finished object. For the very first time, researchers can get the full picture, a truly complete prediction of how that material is going to react. Okay, a computer model is awesome, but it's only as good as the real-world data you put into it. So now we have to go from the digital back to the physical. We need to run experiments, but not just any experiments. We need the ultimate stress test. So here's the thing with the old way of testing materials. It's kind of like being a detective who only shows up to the scene after everything is over. You can look at the wreckage, the post-mortem, but you completely missed the critical moment of impact. You don't know how it broke, just that it did. And when the entire event happens in nanoseconds, the how is everything. And this is where things get really cool. Scientists now have these incredible tools that are basically the fastest cameras on the planet. I'm talking about things like synchrotron imaging, which uses these super powerful X-rays, and ultra-fast electron microscopes. These things let them capture a nanosecond by nanosecond video of the damage as it's happening. They can literally watch a crack form and race through a material in real time. This quote just says it all, doesn't it? It perfectly captures this huge shift in thinking. We've moved beyond just looking at the aftermath. Now it's all about watching the failure live, as it happens, right down to the atomic level. And that's how you find the hidden weaknesses you need to engineer away. All right, so we've got predictive models that are getting smarter all the time, and we've got real-time video of what happens during an impact. Now we get to the fun part, taking all that knowledge and cooking up a whole new recipe for resilience. It's time to actually build these next-generation supermaterials. And the strategies they're using are just brilliant. It's not about finding one single unbreakable material. It's all about clever design. They're doing things like embedding tiny, ridiculously strong carbon nanotubes to act like rebar on a microscopic scale. They're weaving different fibers together to stop cracks in their tracks. And they're creating smart layers, like honeycomb cores, that are specifically designed to crumple and absorb a shockwave's energy before it reaches what's behind it. And let's be super clear, this isn't just some abstract science project. This research has huge, real-world consequences. We're talking about developing much stronger armor to protect soldiers, designing buildings that can actually ride out the violent shaking of an earthquake, and building spacecraft that can survive the punishing journey into deep space. This is science that saves lives and pushes boundaries. So, when you pull back and look at this whole field, what's the big takeaway? Well, the real revolution isn't just in the fancy computer models or the amazing experiments or even the new materials themselves. The future, the real secret sauce, is in putting it all together. Yeah, the blueprint for making this all work is totally holistic. It's about creating this constant feedback loop where the experiments make the models better and the models tell the scientists what to test next. It means you need materials scientists and engineers and physicists all in the same room talking to each other. And it even means looking beyond the single moment of impact, thinking about long-term stuff like rust and corrosion, and so importantly, making sure these new materials can be sustainable and recycled. This final quote just nails it. This whole integrated approach, it isn't just a small step forward. It's promising to completely transform our ability to protect people and the things we build. The potential impact here is just massive, touching everything from our national defense to the future of space exploration. And that brings us right back to that question we started with. For so much of human history, our biggest dreams have been held in check by the simple fact that our materials just weren't strong enough. So I'll leave you with this to chew on. When those limits get pushed further than we ever thought possible, what new worlds will we be able to explore? What impossible things will we finally be able to achieve?